All right, so in this video, we're going to take a look at extreme values. And so much of this comes straight from the ideas you learned in Calc 1 with very, very minimal changes. Now, the problems will get a little bit messier only because you have now more to keep track of, but the fundamental idea is not at all any different. So we'll start off here with some very generic definitions for maximums and minimums. A maximum would be something of the sense that all of the other points are less than or equal to a specific point for all xy ordered pairs in the region. And so we're saying we have a maximum value if that value, now which is now a z coordinate, if that z coordinate at that point is bigger or equal to all of the other z coordinates around it, then of course it would be a maximum. A minimum would be the opposite. A minimum would say that the z coordinate at AB is going to be less than equal this guy right here. So it's below all of the other z coordinates for all xy ordered pairs in region R. So again, very generic definitions for maxes and mins. The extreme value theorem is similar to what you saw in Calc 1, which guarantees both an absolute max and an absolute min on region R, provided it's closed and bounded. Now, we'll have to talk more about this when we get to an example, because there are going to be some slight adjustments we need to take into consideration. But that being said, given our region R is a closed and bounded region, then there will be both an absolute max and an absolute min. So where did these occur in Calc 1? Well, they occurred at critical values, and they occurred at the endpoints. Now, we're just going to say interior points and boundary points. And again, we're going to look at an example here in a little bit that's going to clarify. But these interior points right here, these are going to be our critical points, which used to be our critical values. Now they're going to be critical points because they're going to be AB ordered pairs. Those critical points can be found the same way they were in Calc 1 also. In Calc 1, we took a derivative, set it equal to 0, and solved it. Well, now we're going to have to take the derivative, but we're going to take f sub x at AB and f sub y at AB and set both of those equal to 0 and essentially have a system of equations. Now, this isn't very difficult to understand if you can see a picture. And so the picture I want to refer to you is going to be on page 850 in the text. It's figure 14.44, and it really does a good job in showing you why the derivative, that's going to then be parallel to the x-axis, and the derivative, which is going to be parallel to the y-axis, set equal to 0, will give you a good indication on where we need to study the function itself to determine maxes and mins. So last thing I'll say before jumping into a problem is if there is a z, we would also need to take f sub z at AB, and then you'd have another equation added into the original system that I have up on the screen. All right, so we'll take a look at this surface right here, and we're going to find any maxes or mins. And so to do this, we'll need to start with our z sub x, which is going to be the partial derivative of this with respect to x. So there's a variety of different ways you could take this derivative. I'm just going to go ahead and cut to the chase a little bit by doing a quotient rule. You could see that first term in the numerator would zero out. Then we would have minus a 1 times the derivative from the denominator. And so with respect to x, that's going to be a negative 2 plus 2x over, then we have our denominator squared. So then z sub y would be pretty similar. We would have a negative, and then the partial with respect to y would be a negative 4 plus 4y cubed over that denominator, once again, squared. So if I set both of those equal to 0, that's going to give me those critical values. All right. Now, when I set those equal to 0, we're going to get rid of those denominators. Those are going to go away. And when we solve this top one, we get x equals 1. And we solve this bottom one, we get y equals 1. So that means we have a critical point at 1, 1. Now, the goal here is to figure out, it isn't so much the finding of it, is to decide if it's a max or a min. Now, one of the easiest ways to do it is to graph. Now, I'm not assuming anybody here can graph this off the top of their head very easily, but just using some basic logic, I think we could figure that out. So we know that if we look down here specifically, these x squareds and y squareds are going to be the dominant x's and y's. And so as these values change and get bigger, what's going to happen to the overall z is that it's going to get smaller. So by these being 1s, as they change to 2s and 3s and 4s and 5s and whatever else, this whole thing right here is going to get smaller. Therefore, this would have to be a maximum. So I'll just briefly summarize that our critical point would in fact be a give us a maximum at 1, 1, and then f of 1, 1. I'm not asking you guys, most of the time MML might be different, but most of the time I'm not asking you to compute that. Just give me the z value being f of the point. So that would be a maximum because it opens down. And when I say opens down, I just mean that this thing is somehow dropping below the original 1, 1 on some interval as these values change from 1s to 2s or even negative numbers. Notice they're even powers, so the negatives are going to get eaten up in there and still make this whole thing right here continue to get smaller and smaller and smaller, leaving us with a maximum at 1, 1 f of 1, 1. All right, so in this problem, we're going to take a look at the surface, and we're going to determine all of the points where this surface would have a horizontal tangent line. So we've done these in Calc 1 before. Now we're just going to amp it up here and move forward with z sub x and z sub y both being set equal to 0. So these will both be product rules, and so we'll call this guy maybe our first, and then this guy here our second. So with respect to x, the derivative of the first would be 2y, followed up by the e. So there's the derivative of the first times the second, plus the derivative of the second back times the first. So that first would be a 2xy, and then the derivative of this guy with respect to x, I'm going to go ahead and write that down. It's going to be an e to the negative 1/2 x squared minus 1/8 y squared. And then back times the derivative of the inside, which in this case would just be a negative x. All right, so now to manage the space a little bit better on the screen, I'm just going to go ahead right now and set it equal to 0. And pay close attention. What makes this look really messy is this e and this e. Well, it's in common with both. And e raised to anything is always non-zero. So essentially, you can just divide that off. So that can go away. And then that's the case with all exponentials like this. So don't be afraid of them. Just divide them off. And when we do this, then it looks a lot nicer. We get a 2y minus 2x squared y equals 0. So if I factor the y out and divide off the 2, I'm going to divide the 2 off to get it out of there as well. So factor the y out, 1 minus x squared equals 0. This gives us a y equals 0, an x equals 1, and an x equals negative 1. Now, z sub y, this would be the derivative of this guy with respect to y. We'll go ahead and do it as a product rule in the same way. We're going to have the derivative of the first, which would be 2x times the second. And then plus derivative of the second back times the first. There's the back times the first. For the derivative of the second, I'm going to have this e raised to this big mess. And then back times the inside, derivative of the inside with respect to y. So that would be a constant. This would be a minus 1/4 y. So minus 1/4 y. So there's our derivative of z with respect to y. I'll go ahead and set that equal to 0. And much like the last one, I'm not paying any attention to this whatsoever. When I say I'm not paying attention to it, I mean I'm dividing it off. It doesn't have any influence in my work. So then I have 2x minus 1/2 xy squared equals 0. I'd multiply everything here by 2, which would give me a 4x minus xy squared equals 0, just to get rid of those fractions. Now ready to factor out an x. And we'll get an x equals 0, a y equals 2, and a y equals -2. So let's not forget, we're trying to find where the surface here will have a horizontal tangent line. So working with these partial derivatives, setting them equal to 0, coming up with these numbers, this is going to allow us to put together these ordered pairs. Now, in doing that, we have to be very, very careful because there's a certain there are certain ones that are correct and certain ones that would not be correct. For example, if x is 0, does that mean y is 2, and does that also mean y is -2? If x is 1, does that mean y is 0, 2, or -2, or any of or all of those? So we have to figure that stuff out. Now, fortunately, we have enough clues in front of us to help us out, and I'm going to guide you to look right here. This is where it's going to be very helpful, and this is also where it's going to be very helpful. So I'm going to scoot the screen up a little bit, and we'll take a closer look at these numbers right here. We'll take a look at these and take a look at these and see how to put this stuff together. Well, to get started, let's maybe start with 0, for example. So if x is 0, if x is 0, if I put an x right there, that says that y can be anything, okay? But if x is 0 right here, that says that y has to be 0. If x is 0 here, that's going to give us a 1. 1 times what gives us 0 implies that that y has to also be 0. So the only thing that can be paired with 0 would be 0 itself. Okay? Now, similar conversations can be had about some of the other ones. Let's take x to be -1. Okay? So if x is -1 here. So if x is -1, that says that y can be anything, right? Because it would 0 out. But down here, if x is -1, for this to be true, y would have to be plus or minus 2. So that means that -1, 2 would work. That also means -1, -2 would work. And so now we'll take a look at x equaling 1. So now when x is equal to 1, if I plug that in up here, if x is equal to 1, y can be anything. But down here, if x is equal to 1, y's got to be equal to plus or minus 2, or can be equal to plus or minus 2. So by the same logic here, we're going to have to include 2 more points, 1, 2, and 1, -2. So these would be the 5 critical points. So critical points that stemmed from us taking the derivatives, setting them equal to 0, all because we were in search of the places, 5 places apparently, where the tangent line is going to be horizontal to this surface.